And so begins Chapter 6. We're moving on to new concepts of work and energy. We still are considering forces in this chapter, but now we're going to start taking a look at work rather than using the force to calculate position, velocity, acceleration, time, and all that good stuff. We're going to talk mostly about constant forces in this section, but I'll mention briefly how this works for a varying force. And then we're going to spend a lot of time talking about energy and how that's related to work, this work-energy principle. I'm going to talk about a couple types of energy of things that are moving, or energy that has the potential to do something. Some types of forces and whether they're conservative or not. Mechanical energy and its conservation. Reiterate some problem-solving strategies using using now the concept of mechanical energy rather than using all the kinematic stuff that we are already familiar with. Other forms of energy and energy transformations, and energy conservation when there's forces that are dissipative. And last but not least, a couple slides on power. So in the past, we've been using our forces to calculate our accelerations and then our positions, velocities, accelerations, time, and we've been able to build a fairly good picture about where objects are at any given time and being able to predict how fast they will be going in the future, and so on and so forth. When we're talking about work, the math and the algebra are a lot simpler, but the trade-off is we don't have the detailed knowledge of position and so on and such forth to be able to predict motion nearly as well. So let's jump right into it and ask ourselves how much work is being done by this young lady as she pulls this block from right here to right there using the force of this rope, which is slightly in the upwards direction. So that is our question. How much work did she do? We'll say that it's a constant force. She's not jerking on the rope. The amount of work is equal to the force that is in the parallel direction. You can kind of see a parallel right there, multiplied by how far she managed to drag the box, this distance d. And since we're all super good with vectors at this point, we know that we can break f down into its components and get f in the parallel direction. This is going to be f multiplied by d multiplied by cosine of the angle in between them. I will make a quick note here that both f and d, these are both just magnitudes. The direction essentially has been lost by some more complicated math that is beyond the scope of this particular classroom. What that also says is work right here is not a vector, it is a scalar quantity. I want to talk about now the units of work. The units of work is going to be a joule. It's going to have a symbol of a capital J, and 1 joule is equal to 1 Newton multiplied by a meter, which is about what you would expect because it's going to be a force multiplied by a distance. A joule is simply the name that we attach to this unit of a Newton meter. Now I want to talk about this fella carrying this bag of groceries here. If we were to draw all the forces acting on this guy, we would first draw the weight in the downward direction, the support force of the person. Those two would balance each other out. And if we said that he was going at a constant velocity, then we would say constant velocity, there's not going to be no acceleration, and therefore there's going to be no forces in that direction. both F sub P and M are not in the direction of motion. They have no component in the direction of motion. So therefore, he is doing no work as long as he does not lift the bag of groceries or lower the bag of groceries. In that case, our direction of motion would be that way, and work would be done. Solving work problems is a lot like solving the force problems that we're already used to. The very first thing you do, draw a free body diagram, draw and label all of the forces that are acting on something. Choose your coordinate system, choose it well, something along those lines. Apply Newton's laws to determine any unknown forces. So here we would have maybe, an unknown force, and if we knew that the acceleration was equal to 0, we could write Newton's law and solve for our unknown force. Find the work done by the specific force. If you were interested in net work, then you could find the net force and find out how much work it was done, or you could find the work that was done by each of the forces and add them together. Let's take a brief look at example 6.1 and first start by drawing all of the free body diagram. I'm going to have mass multiplied by gravity, and we're going to have the normal force in the upwards direction, and we're going to have the force of the person right there, and last but not least, we're going to have the force due to friction in the backwards direction. And we know that motion is going to be in that direction right there. So in the positive x direction, we're going to move that box a distance of 40 meters. So let's think about the y direction right here. We could break our force of the person up into its two components right there. I'm not going to explicitly do that in the interest of time, but in the y direction we have no components in the same direction as the distance. So the amount of work that's done in the y direction is all going to be 0. Now in the x direction, we're going to have, let's take a look at the person right here. How much work was done by the person? That's going to be equal to the force of the person multiplied by the cosine of 37 multiplied by the distance that it travels. It's going to be 40, and it tells you what the force of the person is, and you're going to get 3,200 joules. Now let's look at the work that's done by the friction, and this is the one that I really wanted to get to. That's going to be the force of friction multiplied by the cosine of 180. So that's going to be negative 2,000 joules. What the negative means is that it is in the opposite of the direction of motion. And I just wanted to highlight that you need to be careful here, because you don't want to say that the work due to friction is going to be, the force of friction, I forgot my 40 right here, is equal to the force of friction multiplied by the distance, and say, okay, I see that it's in the same direction as motion. I'm going to forget that cosine of the theta. The angle does make a difference. This says that the work was opposing the motion right here, as opposed to being in the same direction as motion. This slide says it again just for more clarification. If the forces oppose the motion, the work will be negative. Let's think about centripetal forces, where the motion is going to be at any given instant in the direction given by the velocity. Now we know that at any given instant that the force is always going to be perpendicular to that motion. So writing work is equal to the force multiplied by the distance multiplied by the cosine of theta. I know that perpendicular means 90 degrees, and we know that cosine of 90 is going to be equal to 0, so the work done is also going to be equal to 0 for any centripetal force right here, because they're always perpendicular to the direction of motion. So energy was actually traditionally defined as the ability to do work. However, we've learned since that traditional definition that not all forces are able to do work. However, in this chapter, mechanical energy only, it does actually follow this definition. So we can ignore the rest of the world for a little bit and define energy to be the ability to do work. What that also would say is the amount of work that is done by something is going to be the change in energy. And we're going to see that here on the next slide. Now, if we consider a car that has some force on it, it's initially traveling some velocity, and it travels over some distance, we know that it's got some force on it, it's going to have some acceleration, therefore it's going to change its velocity. The force was in the same direction as the velocity, so the velocity got larger. Right? We're not doing any type of real rocket science here. However, we could go ahead and we could use our kinematics and say, okay, we know v2 squared must be equal to v1 squared plus 2 times the acceleration multiplied by the change in distance, which will be d. We could go ahead, we could solve for the acceleration, and then we could say, I can figure out how much work was done by saying force multiplied by distance multiplied by the cosine of the angle in between them. I've solved for my acceleration. Use Newton's second law, put that in there, and at the end of the day come up with how much work I did. And that sounds like a lot of work. It is. If we think about what I said in the last slide, where I defined the amount of work to be done as the change in energy, and now I say let me define one type of energy. This energy is going to be called kinetic energy, and kinetic energy is going to be related to 1/2 multiplied by the mass multiplied by the velocity squared. Very important equation here. Then over here I would say I have my kinetic energy 1, which is going to be 1/2 mass velocity 1 squared. Over here I have kinetic energy 2, 1/2 mass velocity 2 squared. And we would say, I know that velocity 2 is greater than velocity 1, so it makes sense that I have more energy over here than I did over here. That jives with what we would expect, because we're applying some force in some direction. We know that we have done some positive amount of work to this car. So we've given it some energy. Now we can write the amount of work as the change in that energy. So work is equal to 1/2 m v2 squared minus 1/2 m v1 squared. That's how much work this force did to this car. So this slide's going to say it one last time because it is such an important principle, this work-energy principle here. The work done is equal to the change in kinetic energy. Written right here, and change in kinetic energy, I've written kinetic energy to be 1/2 mv squared. This type of motion assumes that it's simple left-right object speeding up, slowing down, not going up or down, at least not yet. Now, if the net work is positive, then the kinetic energy has increased. In that case, that's where we've done something where we speed up. The work was done in the same direction as the motion. If the net work was negative, then the kinetic energy increases. That's when something is going to slow down. Example could be, if a car has some friction in the backwards direction, slowing it down, then the net work would be negative. We did a calculation on Ch6a where we came up with some negative work. Better draw the velocity to my car over here and get my labels on here correct so you can follow what I'm talking about. And just to talk briefly about the units, because we can say that work is going to be equal to a change in kinetic energy, then that means that they must have the same units, right? You cannot say that 1 meter is equal to 1 second. You have to say, 1 meter is equal to 1 meter. The units for work and the units for energy are going to be the same. When we work, 1/2 mass velocity squared is equal to my kinetic energy. The units are going to come out in joules.